All right, so let's get started, or let's continue with our exercise from last time. I guess I just said something before we start recording, so I'm just going to mention that again. So this first script here that we used on 0419 was to retrieve the satellite imagery. We did that for the first year, and I assumed that it worked for everyone. And then I asked you all to look into downloading the imagery for 2019 and 2020 as well for this field. And I know on my side I had issues. I think most of you may have had issues as well. And the issue that's going on there is because we exceeded our monthly quota for how much area we can download from Planet for free. So if you remember, we're using the research license, which is free of cost, but really these are commercial products. And so we get a quota of how much we can download for free. And even though our field is not that large, so the field that we're working with, I think it's about 0.4 square kilometers. And we pulled for 2017, I think it was like 47 or something like that images. So if you multiply 47 by 0.4 square kilometers, we're way below our 5,000 square kilometer quota. However, each time that we pull imagery from Planet, if you're pulling imagery for a region that is smaller than 100 square kilometers, it would still count as 100 square kilometers, which was our case for each image. Since we had like 47 dates that we pulled for 2017 times times 100 square kilometers per image, that puts us really close to our limits on the quota. So meaning that most of us were not able to pull imagery for 2019, 2020. However, Clint was able to, so he shared his images with me. I was taking a look at the images, and I'll have more to tell you about that once we finish today's exercise with the 2017 imagery. All right, so again, we already pulled imagery for 2017. That's something that we all should have successfully done. And last class, we started to process those images. So again, the goal that I have here that we're going to finish developing today is a script where we're going to be able to look at those images over time for the growing season. So we're going to be able to understand how the field as a whole, but also parts of the field are progressing over the growing season. If this is something that, if you're working with a grower, or maybe if you're checking for your research plots, imagine that you have the potential of getting one new image per day, and sometimes more than that. Sometimes you may get more than one image per day because maybe more than one of the satellites within those constellations may come over your field. So this is really high dense information. You will never get this density with drones. I mean, you could potentially, but it would be cost prohibitive. Whereas with satellite imagery, it's going to be taking that image anyways, right? So if you have access to it, if you know how to process it, you can use for monitoring that field, or multiple fields for that matter. Also, we can use it for zoning, right? So zoning in the sense of we can extract some statistics from this time series of images and use that to create yield potential zones, as long as we can hypothesize that higher crop vigor, higher green NDVI or NDVI, really any vegetation index, means higher yield potential. So we're also going to be doing that today. All right, so go ahead and start running your code. We have done some of this already last time, so I'm just making sure here I'm getting things started. We did a quick processing for one image, right? So we brought in the first image for 2017. We then we splitted the bands from that stars object. Once the bands were splitted, we could calculate a vegetation index, which you can see how easily that is just typing the formula once you have those bands, right? And if you recall, these names here are because we have those bands as part of that object after splitting. So that's why we're using those names. And then we're just selecting that vegetation index, the green NDVI, to keep forward. So make sure you run that. We explored this image with map view. Again, this was an image from 2017. I think was April 15th, maybe. Let me look at the file name again. Yeah, so 2017, April 21st. This is the image that we're plotting here. So at this point, the green NDVI of the actual field is still pretty low, but we can see some higher points or higher values around the edges, which is mostly related to trees or maybe like a grassy area on this east side of the field or on this west side of the field. All right, so then we talked about, okay, so we just did that for one image. Now, how can we do it for all the images we downloaded, which were 47? So we were developing this code here, and I really, wanna, I guess, explain a little bit more here that what we're doing can be done really for any file type. So imagine if you're doing research, or maybe if you're managing data for a given farm, or maybe multiple fields, and you have like, I don't know, 50 Excel files you want to import, and they all have very similar information, but you want to have all of them imported, you can use a similar approach. So this approach here can be used for any file type. It's not just TIFF. It's just that you have to give the proper pattern, and on the pattern you give the extension. So here we're just looking for all the TIFF files, which are raster type of files that have this pattern in the name. So analytic ms sr clip. And we're looking for that pattern in this folder here. That's pretty much what we're asking here. So if you run that and you print rest list, each component of this list is going to be the path to one of the files in that folder that ends with that pattern of analytics ms sr clip.tiff. If we check the length of this, we already checked that. It was 47 images. And if I just pull the first one for us to inspect the file name, this is the actual file name that it found for the first item. Then we talked about what are the pieces of information, this file name. That string of numbers and how they are organized is something that comes directly from Planet, right? So they have their own pattern of how they name their files, following this convention here. We talked about the convention, which for our case, of course, there's a lot of metadata in this name here that's important, but in our case, really the important piece is going to be this date, right? So knowing that the 4 8 digits are the dates, the acquisition date of that image. We're going to use that here in a second. All right, so I believe this is where we stopped when we were processing all these 46 images. We were getting things ready to import, to read into all of those 47 TIFF files at once. So we started with the data frame where we have a column called source, and that source column has the values of the path to get to each one of those files. And then I was telling you that my goal here in the end is that I'm going to have a column saying date, where I'm going to have, let's say, 2017, 0421, the date, acquisition date of each image. And then I'm going to have a column where I'm going to have that stars object of that date under the column. With that, it means we don't have yet a column saying date. So we were looking for a way to create that column. The first one here that we talked about was using a separate function on the source. And I just want to print here again. So if I just stop right here and I get the first source just for us to look into it. On my side, so I use a Mac. On my side, I have a double / here. So if you change your field name, this name here is going to change. That was our field name, meaning that the length of this string is going to change depending on the size of your field name. And so we couldn't just give a position here. So let's say 80 to 88, assuming that that's the position of the date string, because that would be susceptible to the length of your field and how that impacts the position of the data in this overall string. So then I was telling you that if we can split this and this, then it becomes a lot easier, because if we get this component here in one column, then the first 4 digits of that will always be the date, regardless of our field. So that's where we're doing this separate here. In my side with the Mac, I see a double / here. So if I split this whole string based on that double forward slash, it would work. I remember, if you all remember from last class, people that have Windows, they do not have a double forward slash here. And then Vinicius gave a great tip that instead of using the double forward slash on your separator, you can use 273 forward slash as your separator if you use Windows, as all the files are in this folder and the folder name doesn't change. So if you just use this like 273 forward slash as your separator, it should work on your side. I just want to let it go through that separate. So you see on my side, I'm going to keep the forward slash. That works for me. And I just want to print all images so you remember what happens. So basically the separate created, and I asked it to create two new columns, path and meta. So path is still the whole path to the folder. And then meta is just the file name by itself, right? So now we can come on this column called meta and explore just the 4 8 digits of that string and set that as our date. Can do that now. So I think that's where we stopped. So we use this function str sub, where you give, what it does is you give a column, in this case meta, and you say where to begin and where to end as far as the position on this string, and is going to pull just that sequence of characters, right? So let's say if I wanted to hear the 15, 30, 46, I would have to start at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I will start at 10 and I'll end at 11, 12, 13, 14, 15. So it would be 10 to 15. It would give me the 15, 30, 46. So it's just the position of that character in the string. If I want the date here, is the first 8 digits. So that's why I use 1 to 8. If we just run that, and then we print here all W. Now we have a column that it's still not being seen as a date, is being interpreted by R as character, but at least we know that this is just the date, right? So now we can do some transformations and make sure that R interprets that just as the date. So let me ask, was everyone able to create this date column here looking like this? Or maybe if you were unable, let me know. All right, so the next thing is I want to actually transform this date column to be of a object type date. Right now it is a character, as you can see the CHR. I want it to be interpreted as date. So let's give it a pipe. Let's call it mutate. I want to override it, so I'm just going to call it the same thing. And we're going to use this function called s.date, where we give again what is the name of the column that contains that date, which is called date. And then we need to excuse me, we need to tell this function what is the current date format that this character or this column date is. So if you remember, we talked about date formats, but this case here, we have 4 digits for year. So the way that we establish that in date formats is using a % uppercase Y. So this translates to 4-digit year, which we have here. And then we have 2 digits month, 2 digits day. So the way that we code that is % lowercase m to give us 2 digits month. And to get 2 digits, my gosh, 2 digits day, it's % lowercase d. So if you run it and you print it, and you inspect your date column now, it should be of actual class date, and it should have year / month / date. So this is going to be useful if you need to do any calculations that actually require a date information, right? So let's say if I wanted, for example, if I wanted to calculate how many days there was between the first and last image, you can just do last image, the date of last image minus the date of the first image, and that gives you a duration in days, which only happens if you have the date as class dates. If you have as class character, which is what we had before, it wouldn't work. All right, so really, at this point, I just want to keep moving here with the date column and with the source column. So the source column, if you remember, is the one that has the whole file path or the whole path to the file. So including the folder and the file name as well. So let's just do a select here. Remember, if we're selecting columns, we do select. So I just want to keep dates and source moving forward, just to simplify on our side. So now if I print all images W, I have the date column and I have the source column, and that's it. And 47 rows because we have 47 images that we pulled for this site in 2017. Okay, so right now we are ready to import our data. So if you are not taking my other class, what we're going to be doing next is going to be potentially new to you, and I do want to go slowly there. So again, my goal is on this data frame, I want to have a column that we're going to call image. Imagine a column called image, and then each cell of that column is going to be one stars object. This is a new concept because it's basically data sets inside of a data set. So if it's the first time you're thinking of this, it can be confusing, but we can go through this and explore, try to understand this. So we're going to use here at a pipe, we're going to use a function mutate because I want to create a new column. I want to call that column image. Now, because we're going to be iterating, so here's what we're going to do. We're going to look into the first row here of the source. That is the actual path, again, for where the file lives, that specific file for the first date. We're going to read that file and save that as a stars object in one cell of this data frame. I'm going to then go to the second row of this data set, do the same thing, read this file, and then save that as a stars object under the second row of this data set, under the column that we're creating called image. So we are iterating, we're doing iteration here. We're going row by row in this data set, looking for that path, reading that file that's part of that path, and assigning that to a cell of this data frame. Because we are iterating, we're going to use a function called map. Now, this function has nothing to do with geographical maps. It's not like a map, a geographical, cartographical map. It is a function that is going to map one function to a column. That's where the name comes from. So we're going to call this function map. We're going to give it what column of the current data set I want to iterate over. So that column right now is called source, because I want to go through each item of this column here and import the file that is at this path at each one of these rows. So source is the column name that I want to iterate over. Just break code to make it a little bit easier. Give it a tilde, so that's just the syntax to make this work. And we're going to use a function. So if you think of it, what was the function that we used to read that image by itself? Read stars, right? So we're going to use again that function here. So read underscore stars. And right here where before, so let me just go back to our previous code. When we imported this first image by itself, we gave the whole path, right? We wrote down this path, or we completed using tab to navigate and complete to this path. Now this path is each row of that data frame has a different path for each one of the files. So if I go back to where we were, I really need to put this path under source in here. I have already mentioned on this function map that the information I want to iterate over is under the column source. So the way that the syntax for this works is I just need to basically say to read stars on each row of the column source. And I'm just gonna say .x. So .x is a placeholder for whatever column you specify as the first argument. So we specify source here. .x is just a placeholder for source. That's just the way that we use a map function. All right, so if you run this, it should go through pretty quickly. Just make sure here that you have your tilde. Make sure that you close your parentheses. Make sure you have a .x here inside of read stars. If we just print all images now, I guess it takes just a moment here, but we have that. So now we have 3 columns. We have the date, we have the source, and we have an image column. So again, if you have not seen this before, this is going to be a new concept for you. So notice that before our columns had just a value, right? In this case, it was a string that was related to the path of the file. In this case was a date. Now this new column that we're calling image, because that's the name we gave on the mutate, doesn't have a single value. It has an actual full object, right? Imagine that the image that we imported individually, it is right here. And now the second image is right there. So one way that we can sample or just pull out, let's say this first stars object here, is we can give it a $ image and then use the double brackets notation and give a 1. So that 1 is basically going to the all images W object, going to the image folder and just pulling that first component of that column. Sorry, not folder, but column. So if you just run that, we get this. So we get a full stars object, right? So there is a whole stars object with all of its information, all the pixel, all the CRS, everything in each one of the rows under the column image. I want to take a quick moment here to ask if anyone has any questions. I know this concept is different. These are data frames inside of a data frame, so it can be a little bit difficult to wrap our heads around the first time. So I just want to give a moment if anyone has questions.
Professor Baster.
Yes.
So everything is working fine on my end. I just have 48 photos.
Interesting. I'm not sure why. Anyone else has 48 rows?
I also have 48 photos.
You also
From the
have?
beginning, I'm having it. Yeah.
Okay. So are you guys here in Athens having 48? No. Okay, some are, some not.
They're gonna say I have 48 in Tifton.
Okay. I'm not sure why, because if we use all the same criteria to pull the image from Planet, we should all have the same number. But yeah, I have 47 on my side. I guess for now, we can just keep going. And we can try to understand what are the differences in a moment here. So if I run something on my side and it works on my side and on your side you get an error, maybe if that happens, then at that point we can try to troubleshoot because this error could be related to that difference. But for now, I guess we can just keep going and just, I guess assume that for some reason you got one extra image than I did. All right. Okay, so if you remember when we brought in the image by itself, so let me just go back to that. We read in the image and then we did the following wrangling to it. We split the bands, we calculate green and DVI and only selected that band. So we basically left behind all the bands and only kept forward with the vegetation index. We're going to do the same thing here but applying this individually to each one of our star objects. I actually want to ask you, so if you come here to this chunk, that's the image W chunk. If you have on your outline, you can just click on that image W chunk. You can just copy, starting at that pipe, you can just copy until the end of that select, because we're just going to be recycling this code on the iteration chunk. So copy this, starting at the pipe, ending at the end of that select line, and then go down to where we were. So now I want to have a new column here, where that new column is going to bring in each one of the images, each one of the raster files of the stars objects that we already imported, and is going to apply that wrangling to it. So we're going to give it a pipe. Since we're creating a new column, it's going to be another mutate. I want to call this image_W to mean that it was wrangled. Because we're going to be iterating over all the stars objects that we have on this column that we created on the step prior, we're going to use the map function. So remember, the map function is to iterate over a column. A given function you want to iterate over a column, we use a map function for that. So now, what is the name here of the column that I want to do, that I want to apply all the wrangling steps? So if let me just print here, or let me just get the first rows. Just asking for the first rows here of all images so we can see the structure. So we have date, we have source, and we have image. What is the column that we need to give on this map function that we want to iterate over to do the processing? Image, right? That's correct, because image is where we have the stars objects. We already imported those files using the path, so image is what we want to use. So I say image. Again, image here is because the name of the column that we're going to use is image. So give it a comma. Let's give it a tilde. And really, what we're going to, so if you remember, when we did this for one image, we started with the stars and then gave a pipe and went down. Now, we're not going to say this because remember that we need to use the .x notation to be the placeholder of whatever column you specify on the first argument of that map function. So here we want to say .x, meaning that is a placeholder for the image column, and then you just paste the pipe that we copy from when we did individually on that image W chunk. So now we're just saying, take each element of this image column and then split the bands, calculate gradient DVI, and then only select gradient DVI. That's basically what we're saying here. But then it's going to do this 47 times automatically, right? So the goal here is that we're writing code once that will be recycled, in this case, 47 or 48 times, depending how many images you get. So if you run that and you got your parentheses right, which I hope you did, because we just copied and pasted here. And now we look at what our object all images W is. So we still have a date, we still have the source, we still have the image, and now we have the image W, right? Which is also still a stars object. So it looks, on the surface, it looks very similar. But now let me just pull out the first element of the image W column so we can inspect. So all images, $image W, brackets, double bracket notation, and 1 to pull out that first element of it. So if we look into that, we see that it only has gradient DVI as the band there, which is what we did, right? We split the bands, calculated gradient DVI, only selected gradient DVI for each one of those images. So that's what I would expect. All right, so the next thing that I want to do here is I just want to keep moving forward with two columns, with the dates and the image W column. So if you come after you finish closing that mutate, we just add a pipe here. We're going to do a final select. So dplyr select, I just want the date, and I want the image W object. So if you run that, and then we just get the first few rows or a handful of rows of this object. Now we just have the date and the processed image file. Right, so we left behind our source, we left behind the image column itself, which was just the unprocessed images. We're just moving forward with the dates and the processed image, at least processed to some extent. All right, so if you come to the next chunk here, I just want to do a map view so we can inspect the first or one of the elements of this map. Let's just call a map view here. So I want to plot, if I want to plot just one of those elements under that image W column, we first call the object name, which is all images W. We use a $ notation to select the column image W, and then we use the double bracket notation. I'm gonna ask to look at the fourth row. So that would be 1, 2, 3, 4. That would be the image from May 7th. That's what I want to see on map view. All right, so just going to change here to Esri. We see that, maybe there's not a lot of difference quite yet from the first image that we checked before, which was from April 21st. But just looking at this, I guess there's a couple things that we can notice here. So one of them is that I still have pixels outside of the field. And again, the reason for that is because when we pull this image from Planet, we gave the bounding box of the boundary and not the boundary itself. And that's just how Planet works. They want a bounding box, which is this rectangle around the image. So the next step that we're going to have to do is just clip each one of these stars objects to just the field boundary. Another thing that you may notice here is that there's some pixels missing on that northeast corner of the map. That is probably pixels that were classified as clouds by Planet. And when we use our filter, I think we used, I don't remember now what percentage of clouds we use as our limit, but we use a number there. And those pixels for this date were classified as clouds. Therefore, you don't get them. So Planet removes them from the image before delivering that image to you. Okay, so the next step then for us is going to be to crop these images to the field boundary. That's what we're going to do next here in this next chunk. So I want to assign that to this object called all images crop. Give it an assignment symbol. We're going to call the object that we created above, which is all images underscore W. We're going to give it a pipe. Again, because we're going to be iterating over each one of the elements of the stars objects that we have, we're going to use a mutate where I want to call this new column as crop. So we know it's the cropped image. Now, let me see here. So we've seen already the pattern of how to iterate over a column. I want to ask someone online to help me here with the code of how we would do this. So just want to show you here what all images W is, just the first few columns. So you see what we have available to us. So if my goal is to create a new column that I want to call crop, where I basically want to apply the st underscore crop function to the images. How would you code this? What would be the immediate next thing that you would do here?
I would say map,
Map, right? Okay. Then what?
images W.
Image W.
And now we do comma and tilde
Mm-hmm.
dot X.
Okay, awesome.
And then I think now we're gonna go command again and go call crop
So,
with the buff with the boundary we have.
yeah, I mean, we don't do comma, we're gonna do a pipe, right?
Okay.
Yeah, so imagine that so on the map function, after you determine what column you want to iterate over, and then we give a tilde, and then .x is just a placeholder for that column that we specified. Then within this space here is really the code that you would do outside of a map function, right? So if we're doing this just in a chunk, you would start with an object that was a stars object, give it a pipe, and then use the stcrop function. So thanks, Vinicius. That was really close. Yeah, so we're gonna use the function here st_crop. And then the way that this function works is the first argument is the raster that you want to crop, which is coming through the pipe here and coming as the image W as the placeholder .x. And then the second argument is the boundary, is the vector file that you want to use to crop the raster, right? So imagine we have the raster, we have our field boundary, we're gonna do like a cookie cutter on this, right? We're going to cut that or crop that. So the second argument here is the boundary. That is just an object that we imported earlier on the script, is just called boundary. So if you do that, it's basically applying this stcrop using the boundary to each one of the image W elements, which were already pre-processed by extracting the bands, calculating gradient DVI, and so on. I guess this may take just a moment here to go through. We're gonna wait for that. So we went through on my side. I just want to do a look at the first few rows of this object so we can inspect that. So now we have this crop column is still a stars object because we just cropped it, but we didn't transform it to something else. So it is still a stars object. Let's do the following. So I want to leave behind now the image W column. I just want to keep moving with date and crop. So let's do that because I think that's going to help things to be a little bit faster in the next chunks, as we are not carrying the weight and how much space the image W column takes, because we're not going to need that anymore. We already cropped it and we're going to use the cropped version. So let's just go ahead and give a pipe, ask for a dplyr select, and just do date and crop. So we can go ahead and run that. Let it go through. And then the immediate next thing I want to do is just check again one of those cropped stars with the map view. So while this is going through, we can just think about that, how we would okay, so mine just went through. So what I want to do now is again do a map view. So we call the name of the object that we just created, all images underscore crop. Give it a $sign. We're going to go under the column crop, which is the one that has our cropped stars objects, and use the double bracket notation. And I want to sample here again the image number 4, which was the one that we saw on the chunk above. So if you run that, this is what you should be seeing now. So now we cropped that image by the field. And now we can really pull information about this. So our goal towards the end of this exercise, one of the goals is going to be to extract the median value for each pixel in this field across the growing season. And for that, I do not want to have pixels outside of the field boundary because those are not of interest. It just adds computer power that you're going to require to calculate for those, and you don't really need them. So that's why I wanted to crop that first before doing the next step. All right, so we got to this point here. Now we are ready to do pixel-based analysis. So again, my goal here is going to be to extract pixel level information across all these dates. There's going to be different ways we can use all these images. We have 47 images for the growing season of this field. You could potentially do, different analysis with this data. I want to show you one of them, which is going to be to extract a statistical summary for each pixel across all those images. So imagine that for each pixel within this image here, and I guess if you just come here and you zoom in. So can you see the pixels there? These pixels, again, this is PlanetScope. The spatial resolution is 3 by 3 meters. So each pixel here is 3 by 3 meters. So my goal is going to be to, for each one of these pixels, imagine that if we take one pixel here, and this is just one image, right? But let's say I take, I don't know, this pixel right here, and I have all my dates stacked for this pixel. And I pull the gradient DVI value for that pixel across all images. And now imagine you plot it. Imagine you can plot it with date on the x-axis and gradient DVI on the y-axis. And you can see how this pixel evolved over the growing season. We're going to do that, but for all pixels, right? So not just one. And then in the end, we're going to extract the median of this pixel over time to be a metric that we're going to use moving forward. And kind of summarize 48 or 47 images into one, which is going to be the median of all pixels, or of each individual pixel, but across over time. All right, so before we do that, I do want to change one thing about these objects. So right now they are of type stars, so they are a raster type of objects. I want to transform them to vectors, so into SF, because I think that's going to be easier for us to visualize. One caveat of doing that is that making anything with a vector file type, where each one of the cells is going to become a polygon, that will require more computing power from our computers than if we were keeping that as raster. I do want to show you for this year, for the 2017 year, how to do that on a vector format. And I believe we need to adjust that for the following years. And when we get to those next years, I'll tell you why and how we adjust it. But for right now, let's transform these to a vector file type. So I want to assign that to an object called pixels. We can give the assignment symbol. We're going to start off with the object that we created just above. So that is the all images underscore crop. Now I want to create a new column where imagine that this new column, each cell of that column is going to be that stars object, but now transformed to an SF object. So we're going to get away from stars and transform into SF. So let's give it a mutate. The name of this new column I want to call pixel. As we're going to be iterating over the image W column, we're going to use the map function, or I'm sorry, not the image W, but the crop column, right? So we actually left the image W behind. We're just using date and crop. So crop is the one that has the stars cropped to the field. So we give that name of the column right there, give it a comma, tilde. And then we're gonna, so if you remember, if I want to transform a raster to a vector, what function do we need here? What did you say, Niva? So ST transform is when we want to transform the CRS, right? So if we have like WGS84, we want to transform to UTM, ST transform. But it's close. You're in the right direction. Ujjwal, what do you think? ST as SF, that's correct. So ST underscore S underscore SF is going to transform really any type of layer that has geospatial information into an SF object. In this case, the layer is a stars object, meaning that we don't even have to worry about giving like the coordinates, right? We don't have a column with the coordinates. This is already embedded as part of the stars object. So we just give here .x to be a placeholder for that crop column. And I want to change one argument that's called s_points. S_points. For some reason, the argument is not populating here, but make sure you don't select that function because it is s_points. I want to say equals to false. So if it is true, it gives you the centroid of each pixel. I actually want each pixel to be transforming to a polygon. So s_points equals false does that for us. Now, let me see, if you have not run yet, don't run on your side because I don't remember if this step takes a moment to run or not. It may. Yeah, so I guess what we're gonna do just to avoid like developing one line of code and running and then having to wait for a long time is I'm just gonna give you the full code and then we just run once at the end and I can tell you what was happening each step. Yeah, this takes a little moment here, but it went through. So I just want to show you now on the pixels. If I do pixels, $, pixel, and just pull the first element. It is a simple feature object, right? With, in this case, 44, almost 45,000 features. And that's because we have almost 45,000 pixels. In your side, again, it may be a little bit different because of the way that each of us drew our boundaries separately, but it should be around this number. And then for each pixel, we have a gradient DVI value for this date, the first date on this data frame. Okay, so now let me just, on this pixels object, so right now we should have, let me do an n row here. We should have 47 or 48 rows, depending on your case. Now what I want to do is basically go inside. Let me just show you the first few rows so it's a little bit easier to understand. So for all the 47 images, I want to go inside of here, of this object, of this SF object, and I want to bring it out to the main level of the data frame. So what I mean by that is for each one of these objects, there is like 45,000 rows. I want those 45,000 rows to come out for each one of those SF objects. So then in the end, we're going to have 45,000 times 47. That's how many rows we're going to have in the end. I'm going to bring the data out from each one of these SF objects into the main level of this data frame. To do that, we are going to unnest that column. So we're basically, right now the column is nested because we have these data frames under a column. Now I want to unnest that column. So let's give it a pipe and call the function unnest. So again, on your side, I would recommend you don't run this. I will run this on my side here without saving, just so we can see what happens. So if I just run that, oops, we have to say unnest in the name of the column. So I want to unnest the column called pixel. So if I do that here, I want to show you what happens. And again, if you can wait to run the whole chunk until we get to the end, that's going to be better. So you don't have to wait for the chunk to run each time. We can just do that on my side and see what happens. All right, so almost 2 million rows. Now I have it, notice how I have the date value repeating. This first date is repeating for about 45,000 rows because are all the rows associated with the gradient DVI values for each of the pixels for that date. And then they have a geometry, which is just that polygon, mini polygon that would be each one of the pixels. Right, so we have almost 2 million rows in this data frame. with all the pixels for all the images that we have here. Now, my goal here is gonna be, so here's a way around. So I was telling you earlier that if we use an asset object, one of the downsides of that is that the computational power that it takes to do really anything is gonna be larger demand than if we were using as raster. To avoid that, to avoid having that computational power, one quick trick we can do is just drop the geometry and basically transform that to a data frame by itself. And then do what we have to do and then bring back the geometry. For us to be able to do, because the geometry is really what makes it heavy. It's because it's thinking that, I mean, it is looking at the geometry, understanding its geospatial, and then trying to do a heavier lifting than whatever it needs to. So for us to be able to remove the geometry, do whatever we have to do, and then bring back the geometry and make sure that the pixels match with the proper geometry, we have to have a column that is not the geometry, but that we can use to connect the points with, or the data, the gradient DVI values with the geometry itself. So for that, I want to create a column called Pix ID. So we're gonna give each one of those pixels an ID that's gonna go from 1 to about 45,000. And that's gonna be the column that will translate, or that will be able to connect back the geometry to each one of the pixels in this field after we have dropped that geometry. So let's give it a pipe here. As we saw, maybe each date may have a different pixel number because they have an A's in some of them because of cloud coverage. So let's do a group by date. So remember we have the date column. And then I want to do a mutate that I want to call this column called Pix ID. And I want to say that this number should start at 1, and then you give a colon so it knows that it's a sequence of numbers, and end at the length of NDVI or green NDVI. So what this is doing is it's taking a date, looking at how many rows that date has in this data frame here that I just showed you. Right, so it takes one of the dates, looks at how many rows that date has, and then starting at 1 and ending at the total number of rows for that date is going to give a pixel ID that's going to go from 1 to about 45,000. One thing here is if I do not give it a group by date before, if I don't group by anything, and I just do this mutate, then the Pix ID is going to start at 1 and it's going to end at like 1,700,000 something. By grouping by date, we are confining this Pix ID to be 1 and then ending at 45,000. And then for the next date, it resets at 1 and goes for 45,000 and so on. So that's what the group by is doing for us here. I'm not going to run it yet. I think we have another piece of code in this chunk before we finish. So after doing this, I want to ungroup this data set because it's being grouped by date to do this operation. Now that the operation is finished, I want to ungroup. So just give it a pipe and let's ungroup. We're gonna have to do an ST as SF after that again. ST as SF just to force it back to SF. Because I think when we do a group by and a mutate, we may lose that characteristic of being an SF object. So we're just forcing it back. And then finally, we're going to do a select here. So do a dplyr, select. I just want to keep the date, the Pix ID, the GNDVI, and the geometry column. So this should be all for this chunk. So or for this part of the code here. If you want to go ahead and run it, feel free to do that. It's going to take a moment for that to go through, and that's fine. We can wait here. But now, again, in the end, this object that we're calling pixels is going to have almost 2 million rows. It's going to have 4 columns. It's going to have a date, Pix ID, green DVI, and geometry. And that is what we need to then be able to plot each one of these individual pixels over time. And also, we're gonna use this object to then extract the median of each one of the pixels in the next chunks here. All right, I guess while we wait here, any questions? Anything that is confusing? I'm sure there's a lot of confusing points here because we're doing the map function. But anything that I could help with to understand? Okay, you just finished running on my side. So I'm gonna keep going here. But if you need more time before we start coding the next chunk, let me know. All right, so again, if we just check here how many rows we have, we can use this function called nRow. So we should have the 1,000,000, almost 800,000. Those how many rows we have. And then if we just want to take a look at the first rows, if you print this whole object, it will freeze your chunk because you're printing almost 2 million rows. So a way to overcome that is just asking for the head function, which only shows you the first handful of rows. So if we ask for the head of this object, it is one single SF object, so we do not have any more the nested data frames. It is just one plain data frame. That we have, well, I guess here it says 6 features because we asked for head, but really has almost 2 million. It is of type polygon, so each one of the pixels is considered one polygon. It is WGS84, UTM zone 16 north. And then if we look here on the data side, we have the date, the pix ID, the Green DVI, and the geometry. All right. So I do want to, do not, just a warning here, do not run the next chunk, and I'll tell you why in a second, but just hold on here. So if my goal would be to create a map, so a plot showing each one of these 47 dates, in my case, all of these pixels for each one of the images, so I could check for monitoring, right? So of course, we're looking into imagery from the past, but imagine if this was the current growing season, you could come check there was a new image, download a new image, potentially every single day, and look at how that field is evolving. You may be able to identify stresses very soon before really a grower or a study that you have would be able to, if they're just looking from the ground level. And imagine here, especially if you have a farming operation, if you have many fields, right? So I don't know, let's say you have 20 fields spread across a given geography. Looking at satellite imagery with high frequency would help you to also understand that. We're not going to be doing that here in this exercise, but imagine that you could create a code that you would say, well, I do expect that, the gradient DVI of maybe in the next 5 days to be larger than what it was today, or maybe the one from today to be larger than what it was in 5 days back. So you could create a code that would basically keep track for you on a pixel by pixel basis. How is that pixel evolving? If it is evolving less than the average of the field, you may, and if that pixel is not only just that pixel, but like an area of your field is evolving less rapidly than the average of the field, it may mean that they are going through stress. So you could even set up a system that it would only tell you, hey, there's an issue here because I pulled imagery, I compared this pixel on that date with the other pixels in the field, and I compared that date with the previous one, and I noticed that this is growing at a slower pace. So maybe an area that you have stress, you may need to or check to see if that's actually there and what is going on. So we're not going to develop a full application here to do that for us, but that is something that it wouldn't take a lot of extra code to do some rules like that. So we could be using this for monitoring. Now, this piece of code here takes a while to run. So I would advise you to not run in class. You're welcome to run outside of class if you wish, The code is already complete. But I do want to show you the figure that it produces, which is what we are gonna use here. So I produced that already on my side. That is the TS, so 2017 Green DVI TS for time series. This is what you would have gotten. So it is one image for each one of the fields. You have the date on top, and then you have just a whole bunch of dates, right? So we can really see here, this is green in DVI. The scale here is that blue is lower green in DVI, yellow is higher green in DVI. So we can really see a few things from this time series. One of them is, as we would expect, earlier in the season, we have lower green in DVI. We have some images here that are cut because those pixels were considered as clouds. We have here one image that was almost completely cut out, probably because of clouds. I'm not quite sure why this even made through, because we had a limit of clouds and this definitely exceeds that limit, but it still made through. So that would be one date that we basically can ignore that date or remove from our data set because it has very little data for us. Same as this one here, so August 22nd. Another thing to notice is that, so again, this satellite here has the potential of giving you at least one image per day, sometimes even more than one per day. If you look here, there are going to be some periods. So this is June 8th, June 10th, June 18th. So here's a good example. There were 8 days in between here without a good image the satellite could get for you. So that's one limitation, is cloud coverage. There are going to be other periods here. So July 1, 2, 3, 4, 6, 9, 13, 19, 20, 21, 28. So this is another good example here. Between July 28th and August 18th, there was no good image for us, even though the satellite was collecting at least once per day. This is an issue we have here in Georgia and other parts of the US, is that our summers can be very cloudy. And that is an issue for satellite. That is one of the occasions where drone can help you and can save you. If you need image between, let's say, July 28th and August 18th for this field, you would have been better off going and flying a drone instead, because it would have a hard time getting that from satellite because of clouds. So again, one limitation, cloud coverage. And with the drones, they are able to fly under the clouds. So even though you may have other issues with the quality of the data you get because of the clouds, but at least you get data. In this case here, with an optical satellite like Sentinel-2, you do not get data. And then we can just see, as the crop, so it starts with the green DVI low, starts to increase. We see that there's some spatial variability in the field as that starts to increase. So it's increasing more on the western side than on the eastern side of the field. We see how that is progressing. It seems like it peaks probably around, between mid-July and mid-August, and then starts to senesce, right? So it starts to die off again, and then probably at some time around here is harvested. So we can really see throughout the field this evolution. We can use this for monitoring. We do see what we already noticed from the yield monitor data that we processed for this field. So remember, this is imagery from 2017. We had a yield monitor data from that year from this field. So, we can see here that the overall, especially early in the season, if we look at these first maps, the western side of the field is being more vigorous than the eastern side. So that's something that if you remember, the highest elevation is on the west, the lowest is on the east. There were differences in EC as well. We see those soil gullies signal coming through as lower green in DVI as well. So it's all connected, right? So satellite really can give us a good indication of what's going on. Here, this image, I think something happened, and I'm not even sure if it was the crop itself. My guess is that the way that these areas look like, it seems like these were clouds that were not properly classified by Planet as clouds, because you can see the shape looks like a cloud, or maybe a cloud shadow could be as well, but it was still given to us, right? Another thing that's kind of interesting is this part of the field here as well. It was not suffering before. So this was June 18th, June 26th, and then July 1st, we see this stress. If this area would have persisted as lower gradient DVI afterwards, I would say probably something happened. Probably, I don't know, it could be water related, could be nutrient, could be disease, it could be many things, but something could have happened here. But we get imagery on the immediate next day that signal is not there anymore. So this is also something that tells me that it was something related to either the satellite itself or the atmospheric conditions that caused these abnormal values here, because they did not persist afterwards. This is also something to keep in mind. Satellite imagery is, I mean, any imagery, but in this case here, satellite imagery, can have some errors in it that we need to, keep an eye on and make sure that we remove those dates from the data set or handle them somehow. All right, any questions here? Okay, so let's do this. We identified here some problematic images, right? So 2 of them have very little data, so I want to remove them because they're not really helping us much. This one specifically here has issues with data quality, especially, it seems like it's a cloud related, so I want to remove that one as well before we keep moving. The way that we're going to remove the pixels for those images only is going to be using the date, right? So it's just going to be a very easy filter function that we're going to keep out these images that we identified as being problematic. All right, so let's go ahead. So again, do not run the plot chunk because it will take some time, and I don't want you to be with your console frozen on that. But that chunk above produces the image that I just showed you. So let's go ahead and do some filters, apply some filters here. You know what? Actually, I guess my immediate next chunk is not for filters, for something else. So we're going to apply the filter after this chunk. So on this chunk here, what I want to do is get a sample of these pixels, because right now, we have too many pixels to plot all of them. But I want to take a sample of these pixels and show their evolution over time, over all the images we have. So imagine you're going to have dates on the x-axis, gradient DVI on the y-axis, and we're going to see how a few pixels evolved over time. So let's begin here by calling the pixels object. I want to do a drop underscore NA to drop any rows that have NA values. I want to do a filter here to just keep some of the pixels, because again, if we plot all of them, it's going to take some time. It's going to be too messy in the plot to even make sense of it. So let's just filter just some of them. So we're going to filter by the pixel ID. So the column is called pix ID. If I want to filter more than one thing, I cannot say equals equals. I have to say percent in percent. We've seen this before. And then I want to give a sequence of numbers. I want to use the C function. And really, the pixel IDs I am choosing here are really arbitrary. There's nothing special about that. It could be really any other sequence of pixels. But I chose to go from pixel 5,500 and then use the colon notation to 5600. So from 5,500 to 5,600. So just getting 100 pixels to plot them here. Now let's just give it a pipe. We're ready to get into a ggplot. Well, I guess before getting to ggplot, I just want to show you here. If I just do this, so I'll do a drop NA and just filter, we get, well, we actually got more than what I was expecting. Maybe, not quite sure why, but we got 2,000 or 3,000 rows. Interesting. Well, and then we're just going to plot the gradient DVI over time. So we have a date and we have gradient DVI here. So let's just give it a pipe. We're going to get into a ggplot where we give the AES function to determine what goes where. X is gonna be equals to date, which is a column that we have. Give it a comma, Y is gonna be equals to green NDVI. And I do wanna add something extra here, which is called group. So I wanna group by Pix ID. If you come at the end of that ggplot, add a plus, break code. I want to add a line to each one of those pixels. So let's do a geom_line. I want the size to be equals to 0.1 because again, we're going to have many lines here. And they can look too much. So I want the line to be small. And I also want them to be a little bit transparent. So I want to say alpha equals to 0.5. So 50% transparent. One thing I want to change here is the way that the date, well, you know what? I think this is probably good for now. Maybe we can just stop the code right here. So let's just go ahead and run that. This is going to create this time series for us. So if you see here, these pixels, and again, this is just a sample of the pixels of the field. There are many more pixels here, but overall, they do follow a trend that you would expect, right? So near planting, they're not very vigorous. They start increasing in vigor, you know, it increases into a point where it's probably around flowering and then it starts to senesce. One thing, and of course, like we have some ups and downs here, which, you know, we could argue that maybe this date, whatever that is, we could remove that because it's not natural for a pixel to decrease and then increase again. Unless perhaps it's a light water stress. So maybe that could be the case. However, this date here is really problematic, right? I mean, we really see that, at least for the pixels that we pulled, there's a huge drop, significant huge drop, and then huge increase afterwards. If this drop had happened and then it had not gone up, at least not by how much it did, maybe it was a true signal, but this is also a way for us to think that something went wrong either with the sensor or maybe with the atmospheric conditions or the processing that Planet does on their side. So this date here, I would definitely remove. This date happens to be July 4th. If we just look again in our time series that I showed you earlier. July 4th is right here, which is weird. It doesn't look like that was really the problematic one. It seems like it would be more July 6th. But anyways, we're going to, on my code here, it was showing, I was changing the axis to show what was the date. I did not show you the code for doing that just for brevity, but this was July 4th. So based on this plot and based on the plot above, which takes some time, you did not run, but I was showing you on my side, I want to remove a few images here based on cloud coverage and also abnormal values. So we're going to do that in the next chunk. And just to let you know, after we finish this chunk, I will give you a 5-minute break, and then we'll come back to finish the exercise. So on this next chunk here, I want to call this pixels_f. So we give it the assignment symbol. We start off with the object pixels, and we're just going to apply a filter function. So it's going to be easier for us to say which images we do not want than to say which ones we do want. The way that we do that, or one of the ways that we do that in R, is we're first going to say filter the dates that are equal to these, where these are going to be the bad ones. And then we're going to come back to the sentence and ask it to do the opposite of it. So instead of keeping the bad ones, it will remove the bad ones. It's going to make more sense as we start coding here, but so we're gonna filter by date. So date, we're gonna say in, basically meaning equals, but we use in when we have more than one value, more than one date. We're gonna use the C function. And because this column here is of type date, we have to use the s.date function right here, and then provide the dates we want to remove. So let me pull up my time series again. We want to remove June 8th. We want to remove July 6th. We want to remove October 22nd. And based on the time series of the pixels that we just did, July 4th as well. So let's go ahead and do that. Ask to remove these 4 images. So let me just maybe minimize this in a way that I can see them. So the first one is 2017-06-08. You come outside of that quotation marks, give it a comma and break code. So it's still inside the S date, but outside of that quotation marks. Give it another set of quotation marks. We want to filter out this one. So 2017-08-22. Give it comma, break code again, another quotation mark. We want to remove this one here, 2017-07-06. That's the one that has lots of clouds. We also want to remove the one that, at least on the time series plot, seemed that it was low values. So that is 2017-07-04. So now that I looked at my map, I just will increase this so you can see better. So these are the 4 images we're keeping out. 2017-06-08, 08-22, 07-06, 07-04. And then, so right now we're saying filter the dates that are equal to those. For us to flip that and say, just do not keep these ones. So just do not filter these into the data frame. We come here right before date, we add an exclamation point, and then we have to wrap all this starting on date and ending on the last parentheses of the C. We have to wrap all this. Let me just highlight here. This all has to be wrapped within parentheses. So you add a parentheses right before date and make sure you close that right after at that point. So this is how it should look like. You know, you should have exclamation point, parentheses, and then everything we did. Make sure you had each one of the dates as their own quotation marks, so they're not putting more than one date within the same quotation mark. You have a comma in between the dates. Then you close the parentheses for the asDate function. You close the parentheses for the C function. You close the parentheses for wrapping all that around. And then finally, you close the parentheses for filter. So there's going to be, should be 4 parentheses after the last date. All right, if you run that, we're basically just removing all those images. Now, if we check how many rows, we can check with the function nRow pixels_f. Seems like still the same number for some reason. Let me see the number of rows of pixels only as well. Huh. I don't know why it's doing that. It's almost like it did not filter those dates. No, I did not notice this before. Let me try to see if I can do a quick troubleshooting. I wonder if I'm forgetting. Let me check my code. Oh, yeah, okay. So I think I gave you the C function too early. So actually, if you come back here, delete the C function there, we want the C function to be inside of the S date. That is the only change. Everything else is still gonna close properly, but I think that was it. So I had the C open parentheses before the S date. I deleted that and added after the S date. I think that's what is going on. Yeah, that was the problem there. So just make sure your C function is inside of the S date function, and then you're gonna notice that the number of pixels on the pixels filter, it drops down, you know, probably over 100,000 in number here. All right. So I guess,
And
Hey.
please keep the screen there.
Yeah, and Dr. Bastos, and tipped and R's dropped different numbers. Like ours, it dropped a different amount than yours did.
did you have the same number to begin with? So I had, if I do an in row pixels, which was the one with all the pixels, I had this many. So 1,780,000. I think you may have had more here, potentially because of the extra image that you got on your side. So if you have differences, it may be because of that.
No, I actually have fewer. I've got 100 or 173.
On pixels or pixels F?
Correct. On total, on pixels.
Huh.
On pixels, I've got 173, but then with the pixels F, it was like 150, 158.
Okay, I'm not sure. Also, oh yeah, thanks, Gonzalo. Gonzalo just mentioned a great point. This could also be because of the boundary. Yeah. Because we all have a different boundaries, because we all digitize individually. So if you did, you know, if your boundary size was larger than mine, you're gonna get more pixels. If it was smaller than mine, you're gonna get less pixels. Yeah, so that's a great point. Thanks, Gonzalo. But I mean, as long as you have less pixels on pixels F than you did on pixels, you know, we're doing the filtering, and that's what we would expect at least. Okay, so save your script. The next thing here is we're gonna extract the median for each pixel over time. I do want to give you here a 5-minute break, and then we'll come back and finish this exercise. So let me add here a timer, and then we'll go from there.
Hey, Dr. Bastos, I want to make a question about that code. Are you going to do the mean of the field and extract like the mean of the entire field, or are you just gonna work with like pixels?
We're gonna extract the mean of the pixels or the median of the pixels. Yeah.
So like after that, I can do the mean of the field. Got it.
Yeah, so
If I
the,
want to.
right. So really the only difference there is gonna be what we group by. So, if we wanna get the mean of the field, like the field for each date, then you group by date and get the mean or maybe the median. If you want by pixel, then you have to group by pixel, right? And so it's just the different variable that you group by, and that's the only difference in the code.
Thank you.
All right, so we're done with our 5 minutes here, so let's come back and continue the exercise. Okay, so again, my goal here is for us to go on each one of these pixels and imagine you have a time series over time for each pixel. I want to extract the median of that pixel over the growing season. Before we actually do that, I just want to show you what that means for one pixel only. So what we're going to do here in the next chunk is just going to be an example for us to understand of what's going to be happening behind the scenes. So if you come here, my goal in the next chunk is to extract the median value for one pixel only. And then I will plot that pixel, the time series of that pixel, and show you where that median value was. So let's just extract the median of one of the pixels over the growing season. We're going to start off with a pixels object, give it a pipe. Here is where I want to filter just one of the pixels, again, just to show you an example. So we're going to do a filter. I want to get a pix ID equals to 5500. So I'm just getting one of the pixels of this field. I'm giving a pipe. If I want the median of this field over the season. So if we, you know what, let me just show you what happens if you filter pixels and then do pixels and filter pix ID 5500. We get, in this case here, 29 rows, where each row is one of the dates that we have left in this data set for that pixel. So I have date and I have one value only per date because it's just one of the pixels, right? So for this single pixel, I have 29 observations, one for each one of the dates available, and then the geometry as well. But my goal is for this single pixel here to get the median of the green NDVI over the growing season. So notice that multiple values here, these different values are coming from different dates. So if I want to get the median of this, of the green NDVI of this pixel over the growing season, what should I do here? Sendes, what do you think? Not sure? Doug, what do you think? Not sure? Anyone? Maybe in Tifton? Yes, summarize, right? So remember, every time we want a statistical summary of a column, we need to summarize. in this case here, because I only have one pixel, I don't have to group by anything, right? Because it's already just that one pixel in this data frame. So we can just come here and do a summarize. I want to call this median. And this is going to be the function of the name median of the green NDVI column, because I want the median of the green NDVI column. All right, if we run that and you just print this object, is going to be just a single number, right? Which is in this case for me is 0.63. That is the median green NDVI value of this pixel over the growing season. Now, just for us to create the understanding of what this means visually, I want to plot this. So let's start a ggplot. Where, well, you know what? Before the ggplot, let's do something else. So let's start with pixels, which has all the pixels. Let's filter again by the same pix ID. So filter pix ID equals 5500. So we only keep this pixel again when we're plotting. Add a pipe, and then that's going to lead into the ggplot. So ggplot. So notice how this data set, so the filter pixels is what is coming as a data frame into the ggplot. Now I want to again do a geom line. Let's call AES here. On the X, I want to have dates. On the Y, I want to have GNDVI. So if we just run this, this is going to create for us the time series of that pixel only. You know what? Maybe I'm just looking at this now. Maybe we should have used the pixel filter here. So let's do that. Underscore F. So pixels F on the median. So we get the median based on the pixels filtered. And on the plot, we also do pixels F as well. Yeah, that looks better. So now we actually have the filter images that there's still some noise, but it is not as bad. So now my goal is to get the median green NDVI along the whole season, meaning that it would be a value cutting on the horizontal axis here, right? So if I want to add the value that we actually calculated on the top here, we can just add a plus, do a geom age line for horizontal line, that it has this argument for y-intercept. So our y-intercept is just that value that we calculated on the median. So we call median is the name of the object, and then $ median as well is the name of the column. And I just want to make it color equals red, just to look a little bit nicer. So if we run this, this is what's going on. So for this whole growing season, the median green NDVI value of this pixel was 0.66 or something, at least on my side. And that's what that value represents, right? It's not the lowest, it's not the maximum, it is the median value of this pixel for the growing season. This is exactly what the algorithm is going to do, but for all pixels. Now imagine that, I really don't know where in the field this pixel is coming from. I guess we could plot that and see. It's not of my interest right now, but imagine that this is a high yielding pixel, right? So it's a pixel that this is the signature of the growing season of a high yielding pixel on this field. Now imagine that there was another pixel from a low yielding area that would have a lower, so maybe it starts off similarly. It has a lower peak here. So maybe the peak goes the maximum at 0.6 and then it drops. And then you get the median of that pixel is going to be lower, right? So we're really trying to understand here using the median value and relate that back to what was the median green NDVI, which represents crop vigor. So the more vigorous this pixel was, the higher will be that median value of the pixel. And the lower vigorous it was, potentially giving less yield, then the lower that median will be. So that's what the algorithm is doing for us. So right here, we're extracting something very simple, which is the median. We could do more complex things, which I'm not gonna show you how to do, but just to give you some ideas, is we could potentially extract the maximum, right? So maybe the maximum green DVI value could also represent how healthy that crop was and relate that to yield. Or maybe we could extract the area under this curve. So the taller it goes and the more time it remains as high green DVI, the more area under the curve we're gonna have. So we could extract from this curve different aspects and relate that back to yield. In our case, very simple, we're just doing the median.
My case, I have a sudden decrease near to July.
So your plot does not look like this.
Yeah, I have like sudden.
Still that drop. Did you use the pixels F here and here? So I changed pixels F on the median and also before getting to the Gplot. And then on your side, when you check the number of rows of pixels F, it was less than the number of rows of pixels.
Yeah, it is less.
Okay. I'm not sure what's going on there. But maybe. Is anyone else still seeing that strong drop here that we had in pixels? You're also seeing that on this?
I have a
Yes. Yeah, I've got it also.
Okay. I'm not sure why that is. I guess, for now, I guess we're just going to keep going. If this was your research, I would recommend that you look into that and identify what is going on and fix that.
The ones that have like 14 images, not that.
Yeah, that's a good point. Maybe if you had 48 images, yeah, that could have been the case. So when we get to the end of this exercise, we can try to, if we have time, we'll come and revisit this and see if that's the case and try to, see what's going on there. For now, just so we can finish this exercise on time, I want to keep going. But again, if this is your research, you do want to make sure you follow back and remove any, I guess, bad images before you do extract this. Okay, so now what we did here up here was for one of the pixels. Now we want to do this for all pixels. We're not going to be plotting all pixels, but we're just going to be applying this median function to all pixels. So here's the point where if we do this on the current pixels F object, then it takes a really long time to run because of the geometry itself. So what we're going to do is remove the geometry, keep going without it, and then after we do the median, we'll bring back the geometry so we can see in space those patterns. So for us to basically remove the geometry, I want to create this object here called geometry backup, which is where we're going to keep just the geometry of one date. If you think of it, the geometry is the same for a given pixel across dates, or at least it should be. So we're going to just filter one of the dates and keep the geometry for that inside of this object. So if you get started, we're going to use, we're going to call here the pixels F object, give it a pipe. We're going to do a filter where I want just the pixels for one date. So it could be the first date here. So it can be date equal sign 2017-04-21. So if you just run that, and let's just get, I'm not going to print the whole object, just get the first rows using the head function. So all the rows here have a date, which is all the same date, pix ID, and then GNDVI and the geometry. So what we want really is just to do a dplyr select and just keep with the pix ID and the geometry. That's all we care about. We just need to have the pix ID column here and also have the pix ID column after we drop the geometry. So we have that pix ID column common in both of the data frames, and it makes it easy to just reconnect them. So if you run that, now we just have pix ID and geometry. That's what we need. That's our backup. All right, so now let's go to the next chunk where we're actually gonna be extracting the median for each one of the pixels across the growing season. Give here the assignment symbol. We're gonna start with pixels_f. The first thing that we're gonna do here is drop that geometry because again, that's what makes the processing take a long time. So we're gonna use the function st_drop_geometry. If you just run this and you print the pixel median object, it's gonna have your date, your pix ID, and your gradient DVI, but no geometry anymore. So now it is just a data frame. It's not an SF object anymore. So now give it a pipe. I want to drop any potential NA values. So drop NA on the G and DVI column. Next, and Vinicius, here's where you were asking. We're going, so because I want the median for each pixel, I have to group by pixel, right? So let's do here a group by pix ID, that's the name of the column. So Vinicius, if you wanted the median of the whole field for a given date, you would group by date instead. That would be the only difference here. So now that we group by pixel, we're gonna call a summarize, which is gonna look very similar to the previous one. I wanna call this, the column here coming out of summarize as GNDVI. It's gonna be equal to the function median on the GNDVI. And just to make sure if for some reason we still have NAs, which we should not, I just wanna change NA.rm equals to true. So it removes NAs and gives me the actual median and without problems. So if you run this, and you print what this object is, so I'm getting here, this is actually interesting, and I'm not sure why I'm getting so many rows here, but I'm getting 126,000 rows. Let's see, let me do a quick math here. So 126, 828 times 47. Yeah, this is giving me more number of rows than I was expecting. I'm not sure why. I'll work on this afterwards just to make sure I fix this and I tell you what was going on. We should be getting, I think we have per date, we have like 40-some pixels, 40-some thousand pixels. So I'm not quite sure why we're getting 126 here. Let me see. I'm just gonna do a quick check here. If I do a pix ID equals to 1, in this case, it's just 1. Yeah. Anyways, we're gonna keep going, but I'll get back to this and see what's going on. Just trying to think here, but yeah, I'm not sure what's going on. Anyways, so at this point, so we have the median value for each one of those pixels. I want to bring back now the geometry, which is going to know what geometry is correct based on the pix ID. So for us to bring that back, we just give it a pipe. We're going to use the left join function. And the object we give here is that geometry backup that has pix ID and the geometry itself. And then even though it's going to have a geometry back, but it's not going to be an SF object yet. So for us to transform that to SF, we just do st_s_sf. So if you run that, this may take a little moment here to go through. So it finished going through on my side. It tell me that it joined by pix ID, which is what we wanted. If you print this object pixel median, it's gonna take a long time. So let's just ask for the first few rows with the head function. So now I have a pix ID, gradient DVI value, that's the median for that pix ID. for the growing season, and then the geometry of that pixel. All right, so the last thing that I want to do here is just now plot. I want to see the median, the growing season median value of each one of these pixels as a map. So if you come here on the next chunk, I believe I left you all the code. So we're just doing a GeoMSF on the pixel median, where both the fill and the color are according to the pixel green NDVI median of the growing season. And then just changing the scales here to be varieties, giving a title, giving a theme map, and then changing the location of the legend. So everything here, we've done a lot already, nothing new. If we just go ahead and run that, this is how that looks like. So again, this is the median value of each one of the pixels over the growing season. We clearly see here some areas where, the gullies are very clear. We see higher values overall on this western side. And in the middle here seems like something was going on. Maybe this was an area that had some type of stress during the season. I'm not sure what it could have been, but it could be related to some stress. We do see some striping, and I'm not sure that's actual what the data is actually showing us, or if that is just, the way the ggplot is rendering the plot, but I see some striping. I guess it could also be related to the satellite itself. But overall, we get this pattern here. So one thing that this could be used is if you work in a crop where either there's no yield monitor for that crop, or maybe there is, but you don't have that equipment yourself, you could use something like this, so a median over the growing season, to give you some indication of yield potential, right? So here, the higher median gradient DVI, the more yield potential you would expect for this field overall. So I did bring here one image when we did the yield cleaning for this field, we used the actual, yes, but
So my map is not giving me the very few pixels, like it's completely black. I can't see, I'm not getting that map.
Anyone else having that issue? Of not getting a map like this when you plot the median?
Yes. We didn't have to, you gave us some code. Okay, then it had me.
Yeah, I gave you the code. So it may have been. So did you do a drop NA green DVI here?
Yes.
And did you add the NA remove equals true on the summarize? Did you group by PixID?
And on that, whenever I run, or it gives me pixel median out there, it gives me 120,000 rows.
Yeah, I was getting those many as well, like on the pixel median.
But mine does say, it still has the date in there.
Still
My
has the
date's
date.
the 10.
Okay, did you do a group by PixID here?
It just still shows up the date on whenever I run. It gives me PixID, GNDVI, date, and geometry.
Did you use the summarize here?
Yes. GNDVI equals.
I'm not sure. I can check your code afterwards and make sure that we find what's going on, but it's probably something that happened either on pixel median or on the geometry backup. Could be as well. All right, so I guess coming back here, looking at the median map. So again, this median map is solely based on imagery, right? So it's a median across the growing season for each one of the pixels. And then I left the code here that at least on my side, this is the path to bring the 2017 interpolated cleaned yield map that we derived based on yield data. So this is how the map looks like. I do want to bring them kind of side by side just so we can compare them a little bit more closely. So on the left side, we have actual yield data On the right side, we have satellite-based median value across the growing season. You know, they don't match perfectly. I guess we wouldn't expect that to happen, but we do see some of the similar patterns, right? So we see here, I mean, even on the EO monitor, we see the fingers of those gully areas, eroded areas that on the imagery is actually even finer resolution, which we would expect because the grid that we used in AAA was 10 by 10 meters. The imagery is at 3 by 3. So we would expect the imagery to be finer resolution, so give you more details than our grid that we use for interpolation. We see as well, so this area in the middle here of the imagery that is a little bit lower vigor, we see some of that on the yield as well. And then the areas around it being higher yielding, we also see that. We see that the southern part here is more vigorous in the median and also higher yield on the yield map as well. So overall, there is a good correspondence between the actual yield data with the median gradient DVI value across the growing season. So this again is a way that we can use imagery to give you some idea of which areas are higher yielding and lower yielding just based on crop figure and rather than having a yield monitor data. All right, so the last step here is I just want to export this median layer so we can use in the next exercise. If we come here, we're gonna ask for that object pixel underscore median, give it a pipe. We're gonna use write SF because this is an SF object. We open up that path. I want to get outside of code, go inside of data, and export this as 2017 underscore pixel underscore median dot GeoJSON. And then as always, when we use write SF, I want to change that argument delete underscore DSN equals true. So if you run that and you check on your data folder, you should have now that 2017 pixel median GeoJSON. All right, so that's all that I had for this exercise. So just as a quick recap, we brought in one image, did some live processing, and then we switched, I guess, to a process that would help us to iterate over all images. So we created a list of all the images that we had on file. We used that list on a data frame using the map function to iterate over that list. So we read in as stars, as I read stars. We did the processing. We cropped to the field. We transformed this from raster to SF, plotted this on a time series. Using that time series, we determined which images we wanted to remove based on image quality. We removed those images from the data frame. Then we extracted the median of each pixel over time, and then pretty much plotted that median as well to see how that map looked like in space, and also correlated that at least visually. We didn't do a full correlation analysis, but just visually assessing the similarities between the median gradient DVI and the actual yield clean data for this field. And it seemed like they were matching closely there. So that wraps up this exercise. I do want to say that my goal was here to ask you all to do the same thing for the other 2 years. Clint was able to download imagery for all the other 2 years. I can share that with you so we can work on that. I'm not going to do that quite yet because those 2 years have some difficulties that we did not find in this year. One example is I was working with 2019 yesterday, and 2019 has 139 images. And it has a lot more images because many days have multiple images. So there's like one day that has 4 files because maybe 4 different satellites of the constellation came over and those images were available. So there's gonna be some extra steps there that we did not have to do in this exercise. So I cannot just simply give you that as an assignment and hope that you figure out, because I think it will take some more time to do that. So I'm still thinking of it. My goal originally was that we would do this entire processing for all 3 years. So we had a median gradient DVI for each one of the years. And then we use that to create spatial temporal classes, just like we did with yield, and see how that spatial temporal map correlates if you use yield data or if you use satellite imagery data. So that is my goal. I do want to see if I find a good solution for us to start working on what I just described on Friday and hopefully finish on Monday. But that is my vision here. We'll see how complex the processing has to change to accommodate all the differences of the next 2 years. Anyways, so I guess that's all we had for today.
Dr. Bastos, on the exporting chunk, I got a error and it said it couldn't guess the driver.
It's probably double check that you added the .geojson at the end.
Oh, yeah. Yeah, I had an underscore there.
So that's what we're gonna plan to do. I'll share with you if I do find an easy way that doesn't take long to run for us to address the other objects, the other ears, I will share those files with you before Friday, and then we'll work on them on Friday and Monday. And if not, then I guess I'll let you know of what the plans are. But for right now, we're planning to do this again for the other 2 years. Let me take your attendance. All right, so make sure you claim your attendance, and then I'll see you on Friday. I guess any questions from online? Right, don't hear anything. Any questions here in Athens? All right, thanks everyone. See you on Friday.